All right, so this is part one of Unit 3. This is the last unit in the course and the first video in this last unit. So this first portion of Unit 3 is going to be looking at systems of equations. Now when we're talking about just linear equations, so where our variables have a degree of 1, there are three different methods that we can use. We can graph the two equations to see where they intersect or if they intersect. We can use the substitution method where we solve for one variable in one of the equations and substitute it into the other equation. Or we can use what is often referred to as either the addition method or the elimination method. And that's where you're trying to line the variables up with the same coefficients but opposite signs and cancel out one of the variables and then solve and substitute back in. Now, when we're talking about linear equations with just two variables, there's three possibilities. The first possibility is that the two lines intersect at a single point. When you solve algebraically using either the substitution or elimination method, they would have one solution. You'd solve for a coordinate x, y, and when you solve it, you'll actually get values for x and y. Those are called consistent and independent systems, and they have one solution. Consistent and dependent solutions are where they are the exact same line. So maybe the equation looks different, but if you were to graph them or solve them, it would turn out that they are the exact same equation. These have infinitely many solutions because they intersect at every single point. And when you solve these algebraically, you're going to get something that's a true statement. So something like 6 equals 6 or 0 equals 0 or 5 equals 5, something like that. And you'll have infinitely many solutions. The last possibility is that you have parallel lines. These are called inconsistent systems, and they have no solutions because there are no points where they intersect. So when you solve these algebraically, you'll write no solution, and you'll get something that's a false statement, something like 5 equals 11 or 0 equals 3, something like that. So let's get into solving some of these. And in our first example here, we're asked to solve using substitution, and it's set up for substitution really nicely. We have both of these solved for x. So if x is equal to 3y plus 7, I can substitute that in for x in the other equation. So 3y plus 7 equals 2y minus 1. I can subtract 2y from both sides. I can subtract 7 from both sides. And I have y is equal to negative 8. Once I have my y value, I can go ahead and plug it back into either one of these equations to solve for x. I'm going to use the second equation. It doesn't matter which one you choose. And 2 times negative 8 is negative 16, minus 1 is negative 17. So my answer we're going to write as a coordinate because this is two equations that if we graphed it, we would see the point where they intersect is at negative 17, negative 8. The next example is asking us to solve using the addition method. And what we want here is for our variables to line up to where for either for x or for y, we have the same numbers here but opposite signs. Now, in this case, none of them is that easy to do. If I choose to do that with x, then I have to multiply the top equation by 5, the bottom equation by 2, and one of those will need to be negative. If I try to do it with 3, I'd have to multiply the top by 10, the bottom by 3. They're already opposite signs. So neither one of these is super easy to do. I'm going to go ahead and try to eliminate x. You could do it either way. Negative 5, and then I'll multiply by positive 2 on the bottom. So the top equation becomes negative 10x minus 15y equals 80. And then the bottom equation becomes 10x minus 20y equals 60. And when we add those together, the x's cancel out. We have a negative 35y equals 140. Dividing by negative 35 on both sides, y equals negative 4. And I can plug that into either equation to solve for x. It doesn't matter which one. I'm going to choose the top equation. So 2x plus 3y equals negative 16 my y value is negative 4. So 2x minus 12 equals negative 16. Adding 12 to both sides, 2x equals negative 4, so x equals negative 2. So my answer then is negative 2 and negative 4. You always put the x coordinate first and the y coordinate second. All right, and the third method is to solve by graphing. So here we have two equations, and this equation here, notice that there's no x in this equation. That's just a horizontal line at y equals negative 5. So I'll go ahead and graph that one first. Just a horizontal line through y equals negative 5. And then this equation is written a little bit differently. If I wanted to, I could rewrite it so it was in slope-intercept form. So if I add y to both sides and subtract x from both sides, I have y equals negative x minus 1. And that's a little bit easier for us to graph. My y-intercept is negative 1, and my slope is negative 1. So I can go down 1 and over 1, or I can go up 1 and over 1 that way. Either way, I should have a negative slope, and it should be of 1. So I'm going to do this until I hit the other line. And now I can see exactly where these two lines intersect at this point right here, which is, let's see, 4, negative 5. So that's where these two lines intersect. Now it is possible, all the examples we just saw, they have exactly one point where these two lines intersect, or one solution, but it is possible that we could get no solutions or infinitely many solutions. And so in these next couple examples, we'll see that those things happen. So here it says to use any method. If it says use any method, you can pick. If it tells you to use substitution, then you'd need to use substitution. And it's asking us to determine the number of solutions. Now this is set up nicely for substitution, so that's what I'm going to go ahead and use. I'm going to plug that in for y. So 2x plus 2y equals negative 8. I'm plugging in 3x plus 4. So 2x plus, and then 6x plus 8 equals negative 8. Subtracting 8 from both sides and combining like terms over here, I have 8x is equal to negative 16, so x equals negative 2. And I can plug that back into this top equation here. So y equals 3, negative 2 plus 4. Y equals negative 6 plus 4 is negative 2. So my answer is negative 2, negative 2. I could have plugged it into either one, but it's always nice if y is by itself and you're trying to find y to just plug it into that equation. All right, the next example. Couple options here. First off, I notice here that if I divide this bottom equation by 2, then I have y by itself, and so that would be easy for substitution. Elimination would take a little bit more work, so I'm going to go ahead and use substitution here. I could also divide the whole top equation by 3 to make my number smaller. I'm not going to do that at this point. I'm just going to go ahead and divide the bottom equation by 2. So y equals negative x plus 3, and I'm plugging that in for y here. So 3x plus 3y equals 15, negative x plus 3, and I get 3x minus 3x plus 9 equals 15. The 3x's cancel, and I have 9 equals 15. That is a false statement. That means there are no solutions. Now, I realize for that last example, I didn't write how many solutions. It says to determine the number of solutions. So I could just write one solution. This one has no solutions. And for this last example on this page, it says 6x, 6x minus 2y plus 4 equals 0. And then this one is solved for. So substitution again is a nice setup here. So we've got 6x minus 2 times 3x plus 2 plus 4 equals 0. And then we've got 6x distributing that negative 2 minus 6x minus 4 plus 4 equals 0. And we can see everything cancels out. We get 0 equals 0. That is a true statement. That means we have infinitely many solutions. And sometimes when you have an answer of infinitely many solutions, sometimes some textbooks will want you to also write the equation of the relationship, which would be y equals 3x plus 2. Okay. All right, on to the next page, and what we're going to see here is solving a system of 3 equations and 3 variables. So now it's not just x and y, it's x, y, and z, and now instead of 2 equations, you have 3 equations. It's a little bit more involved, but it's not a lot harder. The math that you're going to need in order to do problems like this is not much more complicated than what we were just doing, but it just takes a little bit longer. So what we're going to be looking for is in all 3 equations, we want to pick whatever variable is easiest to eliminate. So if I look at my x's, if I want to use elimination, which is usually what we use with a system of 3 equations and 3 variables, 2x, x, and 3x. Well, if I have an x by itself, that's a pretty easy variable to eliminate then, because I could just multiply by -2 to get those to cancel and multiply by -3 to get them to cancel here. But I notice here that I have y's where I have all my y's have a coefficient of either positive or -1, meaning I'm not going to have to multiply any of these equations by any numbers in order to get the y's to cancel. So I think the easiest variable for us to eliminate is going to be y, and I usually write that. I'll write like whatever variable I'm trying to eliminate and circle it. That just as a reminder that that's what I'm trying to eliminate. And you have to eliminate the same variable in all 3 equations. So our first step here is to pick 2 equations to start with. Now I'm going to pick the top 2, and I'm going to kind of color code things here as I go. So that'll be this teal color here. And I'm going to use those top 2 equations first. So 2x minus y plus 2z equals 7. And then x plus y plus z equals 2. Y's cancel. 3x plus 3z equals 9. And we'll go ahead and hang on to that. And then for the next step, I have to use whatever equation I didn't use. I'm going to use this kind of purple pinkish color here. And then I get to pick either one of these 2. Now, since I have a negative y here and I'm trying to eliminate y, I'm going to use this equation because they're already opposite signs. So I have x plus y plus z equals 2. And then 3x minus y plus z equals 6. And adding those together, the y's cancel, and I have 4x plus 2z equals 8. We'll hang on to that. All right, so in both of those equations, I noticed that I could make the numbers smaller because now what I'm going to do is I have 2 equations with 2 variables. Both of them have x and z, and I can solve that system of equations. So what I'm going to do here is this equation here. We have 3x plus 3z equals 9. I'm going to go ahead and rewrite that as x plus z equals 3. All I did was divide by 3. And this equation here, 4, 2, and 8 are all divisible by 2. So if I divide that whole equation by 2, I get 2x plus z equals 4. Now my z's are ready to eliminate, and I'm actually going to multiply that equation by a negative. So that'll be negative x minus z equals -3. And now adding, and I'm going to go ahead and just cross this out so you're not confused by that. But now if we add those 2 equations together, the z's cancel, and I have x is equal to 1. So I found my first value here, x. I can plug that into any one of these equations. I'm going to plug it into x plus z equals 3. So if x is 1 plus z equals 3, then subtracting 1, z equals 2. And now if I know x and z, I can plug it into any one of these 3 equations to solve for y. I'm going to plug it into the middle one here because it has the simplest numbers. So x is 1 plus y plus z, which is 2, equals 2. 1 plus 2 is 3, so y plus 3 equals 2. Subtracting 3, we have y equals -1. So just like our other problems, we want to write it as a coordinate, and you want to write it as x, y, z. So our answer then is 1, -1, and 2. That's our answer there. All right, these next couple examples here, we have some word problems, and these are the same types of problems we saw earlier in this course, but when we were solving them before, we had fewer unknowns. Now we're going to have a couple unknowns. We're going to have more things that we don't know, and so what we're going to do then is use a system of equations to solve. So in this example here, we have a chemist working on a flu vaccine, and they need to mix a 10% sodium iodine solution with a 60% sodium iodine solution to obtain 50 milliliters of a 30% sodium iodine solution. How many milliliters of the 10% and 60% solutions should be mixed? Now, you don't need to know anything about chemistry or about flu vaccines or sodium iodine or anything like that. You don't need to know anything about those things to be able to solve this question. Basically, what we have is a mixture of something, whatever that something is. And we have a 10% solution, a 60% solution, and we have a 30% solution that is what we want. Okay, so that's the thing that we're trying to make here. Now, they did not tell us how much of these two solutions. So how much of each solution? So amount of milliliters of each of these solutions. They did not tell us how much of the 10%. So the 10% is going to be X, and then the 60% we'll label Y. But we know whatever we add together there, we want 50 milliliters of the 30% solution. So X plus Y is going to need to be 50. Now, we have these percents as percentages, but we want our percent as a decimal. So 10% would be 0.1, 60% would be 0.6, and 30% would be 0.3. And then these mixtures, it's a 10% solution, a 60% solution, and a 30% solution of sodium iodine. 10% means that 10% of that mixture is sodium iodine. The rest of it is water. So if I wanted to know how much sodium iodine was in this amount of milliliters, I would multiply it by 10%. So the amount of sodium iodine would be 0.1 times X. The amount of sodium iodine from this solution would be 0.6 Y. And then the amount from this one, well, 50 times 0.3 is 15. So we have two equations we can write here. We know that X plus Y, however much of the 10% plus however much of the 60%, we know that when we mix those together, we need to have 50 milliliters. So we know that X plus Y equals 50. And then here, however much sodium iodine is in this mixture, plus however much sodium iodine is in this mixture, is going to give me however much I'm going to have in the end here. And so that gives me my other equation here. So 0.1 x plus 0.6 x, y, not x, equals 15. And when we're working with decimals, we can get rid of those. If I need to move it one decimal place, then I can multiply by 10. And I'm actually going to multiply by -10 here so that my x's will cancel. So when I multiply, that top equation is not changing, x plus y equals 50. The bottom equation, -10 times 0.1x becomes -x minus 6y equals -150. And then the x's cancel. I have -5y equals -100, so y equals 20. If x plus y equals 50 and y equals 20, well, then x equals 30. Now we define x and y. X is the 10% solution, so for the 10% solution we need 30 milliliters, and for the 60% solution we need 20 milliliters. Okay. The next example, we did lots of these earlier in this semester, but again, we did easier versions of them where we had fewer unknowns. Now, this example here says, when a small plane flies with the wind, it can travel 450 miles in 3 hours. So this is one of those distance, rate, time problems. And when we did these earlier in this semester, we set up a chart from the very beginning of the problem. So same chart is going to happen here. We have a trip with the wind and against the wind. And we have rate times time is equal to distance. So we have our plane. This is a pretty terrible picture of a plane, but it's going to this destination. It can travel 450 miles in 3 hours with the wind. So if it's going with the wind, then it will have, it'll be traveling 450 miles in 3 hours. So with the wind, that trip is 3 hours. Going against the wind, when the same plane flies in the opposite direction, it takes 5 hours to go the same distance. So in the opposite direction, now it's going into the wind, and it's going to take 5 hours, and it said it's going the same distance. So the distance for this trip was 450. The distance for this trip was 450. What we don't have here is the rate. And that is going to be determined from how they phrase the question. So it says, find the average velocity of the plane in still air. So just for consistency's sake, here's the plane going back. So let's let x equal the plane in still air. And then y will end up being and the average velocity of the wind. So the velocity of the wind. So that's x and y. So the trip with the wind, you have the speed of the plane plus the wind helping to push it as well. So x plus y. When you're going against the wind, you have the speed of the plane minus the wind slowing it down. So rate times time equals distance. This times this equals this. And we're going to have two equations like that. So here we have 3 times x plus y equals 450. And then 5x minus y equals 450. Now, a lot of times what I see students do right away is distribute these 3 and the 5. But what we can actually do is make our numbers smaller rather than bigger. And both sides of my equation here can be divided by 3, and both sides of my equation here can be divided by 5. If I divide the top equation by 3, the 3 would cancel, and that would become x plus y equals, and 450 divided by 3 is 150. And then here, dividing by 5, well, then the 5 cancels, and we have x minus y, and 450 divided by 5 is 90. And now these are ready to eliminate. My y's cancel out, and I have 2x equals 150 plus 90 is 240. So x equals 120. If x plus y equals 150 and x is 120, then y equals 30. But we invented x and y. We want to make sure we answer the question. So the plane in still air is going 120 miles per hour, and then the wind is 30 miles per hour. All right. So those are probably the two most common word problems that you'll see with this topic of systems of equations. There are other possibilities, but those are probably the ones that you're most likely to see. All right, we're going to look at one more thing before ending part 1 of the video. And here we're looking at what's called partial fraction decomposition. Now, when we, way back in the beginning of the semester, first looked at adding fractions together, what we said we needed in order to add fractions together was a common denominator. So in a problem like this, we would multiply by x minus 5 on top and bottom of the first fraction, and the other one would be x plus 2, because we needed a common denominator. So then that turns this into 5 times x minus 5 over x plus 2 and x minus 5, and then plus 3 times x plus 2, and then we'd have x plus 2 and x minus 5, and we continue that. We'd have a common denominator, then we could distribute, combine like terms, and get our answer. What we're going to do now is you're going to be given something like that answer, which in this case would be 8x, and then minus 25 plus 6 would be minus 19 over x plus 2 and x minus 5. So you're going to be given something like this, and you're going to need to figure out, okay, what were those original fractions? This is harder. Creating a common denominator and adding fractions together is not too bad, but going the opposite direction is definitely more work, and this process is called partial fraction decomposition. That's what it is called here. And in business calculus, you might need to be able to do this. There are some topics in future math classes where you might need this. So basically what we're going to be doing here is saying, let's look at this first example here. We have the answer, essentially, of whatever these two fractions were. And in order to figure out what the denominators were, we'll need to factor the denominator here. So if I have 2x squared minus x minus 6, I can use the x method. 2 times negative 6 is negative 12, negative 1, and you may need a refresher on the x method. So you can go back to earlier videos to do that. Take out the trash, and we have x minus 2 and 2x plus 3. So those are my two denominator pieces there. So x minus 2 and 2x plus 3. But we don't know what the numerators are. We're going to call those a and b. And what we're going to do is go through the process of creating a common denominator on this side. So if I was starting with this and I was trying to create a common denominator, what I would do is I'd multiply this fraction by 2x plus 3, and I'd multiply this fraction by x minus 2 on top and bottom. So that's what we're going to do. 2x plus 3, 2x plus 3, and x minus 2, and x minus 2. And what I have then, on this side, I have 4x minus 15 over 2x squared minus x. And actually, I'm going to write the factored version. We just factored that, and we said that was x minus 2 to x plus 3. And over here we have a times 2x plus 3 over x minus 2 to x plus 3. Plus b times x minus 2 over x minus 2 to x plus 3. So among this whole thing, we have these common denominators. So if I multiplied both sides of my equation by that common denominator, and I'm just going to write CD, then that would cancel out everywhere, and all I would be left with is my numerators. So 4x minus 15, not 5, but 15. And then over here, I can distribute that. I would have 2xa plus 3a plus bx minus 2b. And what we're going to do here is we're going to group the terms with x's, and we're going to group the terms without x's. So here I have an x, an x, and an x. Here I have just a constant, and a constant. So the constant, these two pieces are going to have to be equal to this, and the 4x and 2xa and bx are going to have to be equal. I'm going to work with that part first. 4x equals 2xa plus bx. Every single term has an x. So if I divided both sides of my equation by x, they would all cancel, and I'd be left with 4 equals 2a plus b. If I look at the constant parts here, I have negative 15 equals 3a minus 2b. And now if you just look at those two pieces, what we have here is a system of equations with two variables. I have two equations and two variables. So if I multiply this top equation by 2, then I have 8 equals 4a plus 2b. And the bottom equation is negative 15 equals 3a minus 2b. Adding those together, the b's cancel. I have negative 7 equals 7a, so a equals negative 1. And I can plug that into either one of these equations to solve for b. I'm going to choose the top orange one here, so 4 equals 2 times negative 1 plus b. That's negative 2, so plus 2 and plus 2. 6 equals b. So once I have those two pieces, I can go back to what we started with here in the very beginning and say that this is equal to a is negative 1, so negative 1 over x minus 2, plus b is 6 over 2x plus 3. And it's important to write your answer like that and not just write a or b, because maybe you didn't write this one first. Maybe you wrote 2x plus 3 first, and then you wrote x minus 2 over here. Because there's no way to know which one you would put where. Then your a and b would be switched. What's important is that negative 1 is over x minus 2, and 6 is over 2x plus 3. It doesn't matter what's a and b. So it's just making sure you have the correct fractions here. All right. We're going to do one more example, and then that'll end part 1 of this video. So this next example here, we have a little bit more complicated of an example where we have now denominator and numerator with higher powers. So again, the first thing we want to do is factor our denominator here. The first thing I notice, there's the common factor of x, and I'd have x squared plus 6x plus 9. And if I factored that further, that would be x plus 3 squared, 2 copies of x plus 3. So when you have a single factor that's squared, your approach is a little bit different. So rather than just having two fractions here, I'm going to have one with just an x, one with an x plus 3, and one with an x plus 3 squared. Because it's possible that I could have a denominator of just x plus 3, but it's also possible that I could have one where I have x plus 3 squared. And so instead of just a and b now, we have a, b, and c. And we'll have all three of those that we need to find. But again, our approach is very similar in that what we'll do next is multiply by our common denominator, which is x times x plus 3 squared, and x times x plus 3 squared. That'll cancel out here, and what I'll be left with then is 4x squared plus 10x plus 9 equals, and when this distributes to this first fraction, the x's will cancel, and I'll be left with a times x plus 3 squared plus b. One factor of x plus 3 will cancel, but I'll still have x times x plus 3. And then when I distribute here, the x plus 3 squareds will cancel, and I'll just have the x term, so plus cx. So I can FOIL all of that out. I have 4x squared plus 10x plus 9 is equal to, when I multiply this out, that will be x squared plus 6x plus 9. And so distributing an a on all of that, that will be ax squared plus a 6x plus a times 9. Plus, distributing that bx, I have bx squared plus 3bx, and then plus cx. So again, we're trying to group things, but this time we have more groups. We have the x squared term. So I have x squared, and x squared. And so that'll be 4x squared equals ax squared plus bx squared. And then I have the x terms, so 10x is equal to a6x plus 3bx plus cx, all of the terms with just an x. So I'm going to write 6ax, which is the same thing as a6x, plus 3bx plus cx. And then the last one, 9 equals 9a. So the easiest thing for us to solve here is a. Now I'm going to rewrite those top two equations first. So if I divide both sides of my equation here by x squared, that becomes 4 equals a plus b. If I divide this bottom equation here by x, or the middle equation, not the bottom, x, and the x will cancel, and I'll have 10 is equal to 6a plus 3b plus c. In the bottom equation, if I divide both sides by 9, a is equal to 1. Well, if a is equal to 1, then plugging that into that equation, 1 plus b equals 4, b is going to have to equal 3. And if I know a and b, I can find c. So 10 plus, 10 equals 6 times a, which is 1, plus 3 times b, which is 3, plus c. Well, 6 plus 9 is 15. That's a plus sign, not an equal sign. So we have 9 plus 6 is 15 plus c, subtracting 15 from both sides. C equals -5. So I can go ahead and write my equations from the very beginning again with my a value, which is 1, so 1 over x, plus my b, which is 3, so 3 over x plus 3, plus -9, or not -9, -5, can't read my own writing there. This is a 5. So -5 over x plus 3 squared. And that's our answer. And that's the end of part 1.